Thank you very much for the introduction. And also thank you very much for the invitation to give this talk. So as already said, my name is Moritz Kirste. I work for a company, the company called 취리히 Instruments, and I want to talk to you about mastering the long-lived logical qubit. Well, maybe you know us as a company already. What we provide to the community, to quantum computing, are control electronics. So that means we provide a solution that helps you to run a QPU, a quantum processing unit. Now, what do I mean by mastering the long-lived logical qubit? Well, I'll show you in my talk today. So, to the roadmap to fault-tolerant quantum computing, we first need to solve three major challenges. The first challenge is the fidelity of our QPUs, of our devices, of our qubits. And for this, we need to reach very high fidelities in the end to really get to a mode where we can then scale our quantum computers towards fault-tolerant usability. The next challenge we see is scaling in general. I told you we provide control electronics, and well, if you want to scale, let's say to 100,000 of qubits, to 1,000,000 qubits, then you need to be sustainable in size, in the power consumption, and also in the cost per channel or per qubit. And the third challenge, or the last one, is quantum error correction. Only if we are able to suppress errors up to the level of 10 to the minus 10, only then can we really reach fault-tolerant quantum computing. Now, three challenges. Hopefully, you will see there are also three solutions to these three challenges. But let me share a bit more about the roadmap towards this fault-tolerant quantum computing. The first milestone we need to reach is the long-lived logical qubit. For this, it needs to be stable and robust. We can enable decoder research, and then afterwards, we can focus on connecting more than one logical qubit towards what is then can be called logical sequencing. Also for this, we will need to be able to connect to a high-performance computing center, for example, in a so-called loose coupling or in a tight coupling. But only after this, after we have proven as a community that this is possible, only after that we can then really focus towards hundreds of logical qubits or 100 logical qubits, and this, or for that, it's really needed to focus on industry-ready scaling. So really large number of channels. Now on purpose, I didn't put any timelines to this, because honestly, no one in the field knows. But what we can do today, we can focus on this very first milestone. And for this, I would like to share with you a little bit of the story, how we got here as a company. So already back in 2018, we released as the very first generation of commercial available control electronics with multiplex readout established as a standard back in 2018, our very first generation of control electronics. Then in 2020, we released the very first IQ mixer-free control electronics, followed by a milestone in quantum error correction, which was the very first logical qubit based on a surface code. People in the audience will see it's not yet a long-lived logical qubit. And the next milestone we could reach then with our newest generation of control electronics was the record 2-qubit gate fidelities measured at RICON. And last in this line, also mid-circuit measurements done with real-time feedback, which is a big step towards quantum error correction. But as you can see here from this timeline, every 2 to 3 to 5 years, we come up with something new. We come up with a completely new technology to the market. And this new technology we have released just as of this year in March, and that is the tool which we actually call the tool to master the long-lived logical qubit challenge. So you can see here, this is the new generation of control electronics. You can see that's a really enterprise scale system with a lot more challenge channels focused on these three major challenges which I mentioned before: fidelity, scaling, and quantum error correction. And let me show you a little bit more about that. So first, fidelity. Why is fidelity needed to be supported by the control electronics? Well, only if your analog specifics or your analog specification is never a limiting factor towards high or long decoherence times, only then can you really guarantee high fidelity. And what we have here as a new solution is a solution which provides, in the first Nyquist zone, direct digital synthesis via the whole frequency range. It provides the best possible signal-to-noise ratio currently available, very high phase stability, and together with that, you can then really support 5/9 of fidelity. So that's the first challenge. The second challenge was scaling. And here I would like just let the picture speak. You can clearly see on the left side, you see previous generations. On the right side, and the picture is up to scale, you can see our new solution. It fits into a 19-inch rack, and you can easily see that this is a totally different game in scaling, because everything you see on the left side fits totally into what you see there as a single chassis. And the third topic was quantum error correction research. So the system provides you with that functionality by doing two things. The first thing is a very powerful FPGA, which you can use to program your own decoder inside. So you see here, it's a slot card-based system. So in that slot card in the center, you can use the FPGA to program your decoder and use, for example, for real-time decoding. But this card then connects in a full mesh link all the other cards in the shelf, so you can measure data, let's say from a certain readout in your QPU, pass that data to the central unit, and pass the decision back into the system. So that's what we call the full mesh link. But that's not enough. I told you before, for example, a connection to an HPC center is important. You need a connection maybe to a GPU or a TPU or a CPU. So here we provide a connection in which you can use remote direct memory access to directly insert, for example, different data from the system to the HPC center and back. And here it's very important to focus on a very fast round trip. But you might wonder, okay, 364 channels, that's not enough. I agree, that's not enough. So therefore, this system is designed in such a way that you can now also combine not only one of these boxes, but you can actually use it to combine more and more of these boxes. And like you can maybe imagine it like a tree with all the different branches, which are all connected to each other with one root in the center, which is the first central unit. And then all these systems together, again in a full mesh fashion, they can talk all together. And they can also all talk to, for example, an HPC center or a GPU cluster. So with this functionality, we can really enable what a lot of people nowadays call hybrid quantum computing or hybrid quantum classical computing, or you can also call it heterogeneous computing. So that's enabled with this functionality. Now, I want to also tell you a little bit about success stories and results, especially from Korea. So I will switch gear a little bit away from, let's say, the newest release on the control electronics sides to 2 or 3 small success stories I would like to share with you. The very first one is one done together with SKKU, where they are designing their new TUPA technology. It's a topic which also focuses on this challenge of fidelity. And in that case, they have designed their own TUPA. Together with our control electronics, they could measure a readout fidelity up to 99.5% or max even 99.76. And I have to thank here Professor Yonuk Chong and everyone from SKKU for these very nice results. Another nice result from the same university, again SKKU in the lab of Professor Yunuk Chong. Again here, they focus on novel QPU technologies, novel qubit technologies, and in that experiment they wanted to have measurements of very high coherence times. And you can see here as a very nice result the T1, T2 star and T2 echo measurements with very long times. So that's the first success in Korea together with our instruments. But let me share another story or another success with you. That's together with Chris. I think you're all familiar with the institute. And in that collaboration with Chris, we focus on helping them to do a full automated bring-up of their QPU. In this case, it's an example of a 5-qubit QPU, but you could also do it for much larger QPUs. And the idea here is that you have zero human interaction to characterize the typical experiments which you need to do during the so-called bring-up and characterization of the QPU. And a couple of standard experiments, as you can see them described there, they can be done, in this case, in less than a minute time, and there's zero human interaction. And to give you a little bit of a feeling how that really works, we took a video or a screenshot video of this. So let me just go there and start that video. And while the video is starting, I can start explaining it a little bit. So you see on the left-hand side how the actual software is started in Python code. By the way, this is all under an Apache license. So all of this you can use directly together with our instruments as an open source software. And on the right-hand side, you can see how it's working. So all the nodes are followed through. And you as a user, you can click on these nodes, or our partners there at Chris, and you can see for each and every node what exact experiment has happened behind that. So each of these little nodes in this graph represents a characterization experiment, and it's fully automated, the whole running of the experiment, the analysis of the data, and then the decision when to move to the next experiment. So for some of the mathematical people here, it's a directed acyclic graph, as you all will recognize, and this really helps then, in the end, to do this full automation. Well, with that success story, I would also like to wrap up and come to an end. Many of the things I have shown you today, especially also this new control electronics, we also have here at our booth A19 a live demonstration of some of the features which I've shown you. So if you want to check it out, come to the booth A19. It's actually the other hall, just at the very beginning, and we can show you there also this, for example, automated bring-up. But again, what I want to emphasize is to master the long-lived logical qubit, you need to solve those three challenges. You need to solve the challenge of high fidelity, you need to solve the challenge of scaling, and of quantum error correction. And for this, the solution we have now here available for everyone in the community. With this, thank you very much for your attention. Thank you very much. Hope to take any questions if we have time. Thank you. There's a small change. I think normally they don't have questions, but if you have a question, please feel free to ask. I on purpose planned that if you have any questions, you can have. And there's a person with a microphone over there, so if anyone has a question, please go ahead. All right. Well then, no one seems to dare. Then again, thank you very much for your attention, and see you soon. Bye.